Have you ever considered what happens when artificial intelligence starts conducting its own scientific research? Really pushing discovery beyond what humans can manage alone.
It's a fascinating, maybe slightly unsettling thought, isn't it?
Absolutely. So today we're taking a deep dive into something researchers are actually calling an AlphaGo moment for model architecture discovery.
Mm.
Our mission is to unpack this groundbreaking system they've named ASIRC. It's designed to basically shatter the old way of doing things at human-limited pace of AI innovation. And we're basing this all on a really interesting paper. AlphaGo moment 2i507.18074v1.pdf. So let's start there. What's the core problem ASIRC is even trying to solve?
Well, the paper jumps right into it. It highlights this major bottleneck in how AI research gets done. Essentially, it says the pace has been, and I'm quoting here, linearly bounded by human cognitive capacity.
Linearly bounded. That sounds
It
limiting.
really is. Think about it. They mentioned human-only research taking maybe 2,000 hours per model.
Model. 2,000 hours. Wow.
Yeah, and that's just inherently unscalable, right? Especially with how fast everything else in AI is moving. It's just too slow.
Okay, that makes sense. So it's not just about speed, it's like a fundamental barrier.
Huh.
How does ASIR, artificial superintelligence for AI research, how does it actually break that? What does it do differently?
This is the key part. It's pitched as a complete paradigm shift. We're
Yep.
moving, they say, from automated optimization to automated innovation.
Okay, innovation, not just tweaking.
Exactly. So ASIRC can autonomously come up with totally novel architectural concepts for AI models. Then it actually writes the code for them,
It writes the code.
implements them as executable code, yes. Then trains them, tests them, validates the performance, and crucially, it learns from both human knowledge, what they call a cognition base, and its own past experiments.
Its own experience. Okay, so connecting this back, the results must be pretty impressive then. This is where that AlphaGo moment comparison comes in, I guess.
Absolutely. The scale is just,
Mhm.
well, huge. ASIRC ran 1,773 autonomous experiments.
1,700. Okay.
Over 20,000 GPU hours. I mean, that's a massive amount of compute focused just on research itself. And the outcome, it discovered 106 innovative, state-of-the-art SOTA linear attention architectures.
SOTA linear attention. For listeners, linear attention is a big deal for efficient AI, right? Especially for scaling things up.
Precisely. It's a very important area for making models more efficient and powerful. And ASIRCH found over 100 new top-performing designs.
So the paper claims these AI-discovered architectures aren't just slightly better, but they systematically surpass human-designed baselines. Is that hyperbole, or are we seeing genuinely new ideas here?
The claim is pretty strong. They say these architectures show emergent design principles, like AlphaGo's famous Move 37 that sort of baffled human Go masters at first. It suggests the AI is finding strategies humans hadn't conceived of.
Okay, emergent principles. And what was the really big takeaway from all this number crunching?
I think the most profound thing is that they established what they call the first empirical scaling law for scientific discovery itself.
A scaling law for discovery. What does that even mean?
It means they showed empirically that architectural breakthroughs can be scaled computationally. More compute power doesn't just mean faster training. It means more discoveries. It reframes research from being limited by human thinking time to being a computation-scalable process. Their summary is catchy. More computation, more discoveries.
Wow. Okay, that is a huge shift. So how does it actually do this? What's under the hood? You mentioned it learns.
Yeah, the system works as a closed evolutionary loop. Think of it like a cycle that constantly improves itself. There are three main parts, or roles. You've got the researcher, which dreams up the new architectures.
Okay.
Then the engineer, which takes those ideas, codes them up, runs the tests in a, quote, real code environment.
And this is the part that fixes its own bugs.
That's the remarkable bit, yes. It apparently debugs its own implementation errors, which is pretty sophisticated.
That's amazing. Less time debugging, maybe? Sign me up.
Indeed. And finally, there's the analyst, which looks at the results, synthesizes the insights, and feeds that back into the loop. And it all draws on that cognition base, the human knowledge, and its own growing experimental history.
Right, that blend of human input and its own learning. But you said it learns from its own experience. Was there anything particularly surprising about where the best ideas came from?
Yes, and this might be the deepest insight. While it uses human knowledge, the paper states that the really top-performing, the SOTA architectures, like one they named PathGate FusionNet, showed a higher dependency on empirical analysis.
Meaning it relied more on what it learned itself?
Exactly. Insights derived from the AI's own previous experiments were more critical for reaching that top tier of performance than just relying on the initial human knowledge base.
Hmm. So for true breakthroughs, the AI learns best by reflecting on its own results.
It strongly suggests that yes, self-reflection and learning from its own empirical findings seem crucial for pushing the boundaries beyond known human designs.
So this deep dive really shows AI shifting gears, doesn't it? From just a tool that solves problems we set to potentially an autonomous innovator, one that can accelerate its own progress, find things we didn't even know to look for.
Precisely. It's a significant step towards AI actually driving scientific discovery itself, finding these new architectural principles.
It really makes you wonder then, if AI can autonomously drive its own breakthroughs, discover these scaling laws for scientific discovery, what does that free us up to do? What new frontiers open up when research speed is tied more to computation than human brain power limits?
That's the big question, isn't it? Definitely something exciting, maybe a bit daunting to think about for the future of science and ingenuity.